Oh, Jake, can you hit my projector, Todd? Okay, so we're going to start looking at Chapter 7 today. In this, we'll also do just torque. So we'll go to Chapter 8 and do torque and maybe like one or two other very small things. Okay? Torque. Okay. So first, I wanted to talk about the importance of conservation laws. So, conservation laws, like the one that you saw, the one you guys saw was what? Conservation of energy, and you saw it in two forms. You saw the conservation of energy like in general, that it's conserved, and that was there was a talk about how it took them a long time to figure that out because of what was kind of a kink in the works. Diminished dissipated forces like heat, right? That was a long time. It took them a long time to overcome that in developing conservation of energy. There's other conservation laws in physics too. The conservation laws are hugely significant to physics and engineering. So you saw one of them was conservation of energy, but energy is not the only type of quantity that's conserved. So there's energy that's conserved. Today we're going to, in the next couple days, we're going to talk about some other things that are conserved. So it turns out what's called linear momentum. You guys, I'm sure, have probably heard of momentum. We're going to look at what momentum is. That's also conserved from one point in a system to another point, as long as your system is what's called closed. Okay. We're not really going to look at it too much this year, but there's also angular momentum. It's conserved. Let's see. And then later this year, we're going to learn about how electric charge is actually conserved as well between 2 points in a closed system. Okay, so I guess I should write that down. This is only for closed systems. So we're going to have to, we've already kind of hinted at what that is, but we should talk about that more too. Maybe we just should put it down here. I think I have it somewhere else, but so let's put a couple definitions there, I guess. So one definition, I think it's later on in the chapter, but is a system. I've been mentioning this several times. Well, what is a system? So a system is just a collection or a set of objects. So some collection of objects, and we're trying to observe how they're interacting with one another. But we can't talk about like stuff outside of the system. So if you want to think about like 3 different marbles, then you better be talking about all 3 of those different marbles. So yeah. So it's whatever we choose to observe interacting. So we've just got to be careful to make sure we list all the things we're thinking about. Another definition, the book calls it an isolated system. I'm obviously calling it closed. So isolated, closed, they mean the same thing. So this is a system in which let me write it down. That's the way I defined it. I think the book does it differently. I thought this made more sense. So an isolated or closed system is one where the forces that you're thinking about coming up are only between the system objects. That means you can't think of like some kind of outside force interacting. If you think that you need to include an outside force, what should you do with your system? You should redefine it, expand it, yeah. So Let's put no outside forces, no outside stuff.
Like gravity.
Right. So these conservation laws only apply to systems that are closed. So you have to select a system that's closed before you can use them to solve problems. Okay? So if you've got friction or some kind of other dissipative force, like a person doing something, you've got to be careful to consider that. And sometimes you just can't apply these. So if you've got a system that definitely just isn't closed, no matter what you do with it, no matter how you expand it, you just can't apply a conservation law. So that's another thing too. Okay? So let's see, what else do we have? All right, so momentum. So we're going to look at momentum. That's what we're going to look at today. Yeah. So we'll talk briefly maybe about angular momentum, but it's a little bit tricky, and I'm just not going to, it's not on your AP exam or anything, so I'll mention what it is and maybe do a demo, and that's kind of all we'll do with linear, angular momentum. So what is momentum? Anybody have a sense of what it is?
Inertia.
It's got a direction? Inertia?
Is that something kind of,
It's kind of like inertia, yeah.
kind of like when, but like when you're moving, the difficulty is stops.
Yeah, that's good. Difficulty to stop something is a good way to say it. It is a vector. It follows the direction of the velocity. I think someone was trying to say that. It follows the velocity vector's direction. So we want to get that down. And how big is it? So it has magnitude. So P is what we use for momentum. Okay, in physics, P is momentum. It has a magnitude of the mass times the velocity. That's what momentum is. So the way I always think about this, and we'll have a couple videos that we watch and stuff, is if you have a car, for instance, let's say you have a little tiny sports car and you have a great big truck that are speeding down the road. Is it possible for those two things to have the same momentum, even though the car is really, really small? Yeah, no.
Or velocity.
Right, so a sports car could have the same momentum as a huge big semi-truck. It would just have to be moving faster. So if the semi-truck, let's say we have a truck over here, beautiful drawing.
Could be made out of fiberglass.
Let's see, what do you guys think is a good weight for a truck?
10 pounds.
10 pounds?
100,000 kilograms.
10 tons maybe, I
10
think.
pounds, yeah.
And a car,
Half
One
ton.
ton.
Not even half, no, not even just one half ton.
cars weigh like 1,400 pounds a lot of the time. That's like less than 1 metric ton, so maybe just one.
Yeah, if that person decides that's one ton.
That's a pretty big truck. You know, like they say that on trucks, right? Like half ton, 3/4 ton trucks. They say that, right? But anyway, so a ton is not unreasonable. So how much faster would this have to be moving to achieve the same momentum this guy has? 10 times faster, right? Because there's no like scale factors in there. So this guy would have to be moving 10 times faster. So if this guy hits you on a bicycle and he just barely nudges you, it does a lot of damage, and that's because of the momentum that he has, because of his mass. If this guy hits you and just like nudges you and he's only going like, you know, a couple miles per hour, you might not fly, but if this guy hits you because of his mass, you're going to go a lot farther, and that has to do with the momentum. Okay? So that's one thing. So that's momentum. Something you should know about momentum is Newton's second law. When did Newton first write down his second law of motion? What were they set out in? When did he write them down? Remember his great book? Like the most best book of science and math ever written. It was called Newton's Principia. In his Principia, did he write his second law as F equals ma?
Probably not.
Probably not. Like most of the time, those guys had much more cryptic language, and it was much more difficult, and they didn't care how many people understood it, because, you know, they even have a vested interest in keeping the secrets to themselves, and why would they bother with that anyway? You're supposed to be smart enough to figure it out. But one of the things is, it wasn't written as F equals ma, it was written as the sum of the forces, and it was written in terms of momentum, actually. So F equals ma can be written as the sum of the forces is the change in momentum over the change in time. That's another version of F equals ma, and that's the way it was written originally in Newton's time. So you can derive F equals ma from that. Should we try to do that? I think we should. So change in momentum equal over change in time. What is that? How else do we write that?
P2 minus P1.
Yeah. You go like P2 minus P1.
T2, T1.
Sure. What do we just say momentum is? Mass times velocity. That should make sense. I mean, if you think about a truck and momentum, like mass, it's mass times velocity. That's its product. That makes sense to me. So mass 2, velocity 2 minus mass 1, velocity 1. Maybe we need to leave those times like that. Maybe we need to leave them as delta t. I don't know. What do you guys think? I don't know. Let's see. So if we're thinking one object, should I really write these as two different masses? If we're thinking like the momentum of one object?
It's the same mass.
I think it's like the same mass. So let's do that. So I could do what with that mass?
Pull it out.
Factor it out.
What if James Bond jumps under your truck as you're driving under a bridge?
We're just thinking about the truck. There's no James Bond. Not yet. It's pretty funny though. Okay. So what have we got here?
Change in velocity.
You could write this Paul's way or just leave it as change in time. We're all comfortable with that, right?
Could we go?
So what happened? What's this?
Change in velocity.
Yeah.
Acceleration.
What's change in velocity over change in time?
Acceleration.
So that's m. Oh. So that's really just F equals ma, right? So that's the way Newton originally wrote it. It turns out momentum is a lot easier to work with in a lot of situations. So for whatever reason, he chose to write it that way, and I'm sure he solved some problems in the Principia with the other way, but that's the main way that he used it. So let's see if we can find an example or two where we can use that. Let's look at 7.1 in the book. So you don't have to write a whole bunch down. So let's look at 7.1. Do 2 or 3 examples today. Let's try it. Someone want to read? Or I can read. I'll read so the video picks it up. 7.1. We're on page 169. Okay. Force of a tennis serve. For a top player, a tennis ball may leave the racket on the serve with a speed of about 120 miles per hour. That sounds right. I can serve at about 95, 105 in that range.
Okay.
I'm not Serena Williams, though, you know. Okay. So they say 120 miles per hour. Okay, then they converted that to meters per second. If the tennis ball has a mass of, let's get our stuff down. So we've got a mass on the tennis ball of 0.06 kilograms, and we've got a velocity of 55 meters per second. Those are both SI, so we're good. And it says it contacts the racket for about 4, so that's a time, right? 4 microseconds, 4 milliseconds. So that's going to be 4 times 10 to the negative third seconds. That's how long the ball is actually on the racket. So their question is, estimate the average force on the ball, and could that actually like lift a person if it was like applied to a person that weighed 60 kilograms? So, the force on the ball, you could go F equals ma, except you don't have an acceleration, you have a velocity. Well, now when you have that, you can just use the momentum version. So the force is going to be what? mv minus mv over change in time. Change in time was that 4 milliseconds. And where should I put 55? So this is like the final velocity, minus the initial, right?
The first one, final velocity.
The
Because it
initial
says leaves the racket.
It says it leaves the racket, right? So this is going to be like 0.0655 minus.
initial be 0.
What's up?
Wouldn't the initial be 0?
Yes. So what do we get? What they get?
800.
So that's how much force that tennis ball has. So the question is, would that be enough to lift a person? So you've got a person over here.
So now you can do.
They weigh 60 kilograms. Is that enough to lift them? Well, gravity is pushing down with how much? mg, so we've got 60 times 9.8. What's that?
I got 600 newtons.
You could just estimate that as 10, and it's like 600 newtons. So that force generated on the tennis ball is actually enough to lift the person up. It's crazy, right? 60 kilogram person, I don't know. How heavy is that? I'm not sure. I don't know my kilograms. How many? So you go, wow. Yeah, 140.
So.
Those tennis serves are powerful. Okay, let's look at one more, and then we'll go. We'll wrap it up for today. Let's look at 7.2.
Is this enough force to
7.2. Washing a car, momentum change and force. Water leaves a hose at 1.5 kilogram per second. That's kind of a weird unit. It says it has a speed of, so initial speed is what, 20?
Yeah, 20 meters.
Okay. Let's see what else. It's aimed at the side of the car and the car stops it. What's the force exerted by the water on the car? Okay, so I'm going to draw a little picture. So there's water going over here, right? The initial velocity is 20. What's the final velocity when it hits the car?
0.
Okay. So did they tell us anything about a time?
There's seconds in your kilograms.
There is seconds in there. That's kind of strange, right?
Yeah.
So we're going to use momentum to solve this problem. So you've got momentum equals mass times velocity, right? So if you're going to go like this, then you've got the change in force equals change in momentum over change in time. So somehow we're going to have to resolve that time, aren't we? Does that make sense?
How do you convert volume per second?
Right. So let's see if we can get the top part first, and then we'll worry about the time. So I think it's just like the way they said it is strange. So final momentum. What's the final momentum going to be over here?
So we can just call our time a
0.
second, can't we?
Final momentum over here is 0. Initial momentum is going to be, did they give us a mass? They gave us this, right? This has like the mass and the time embedded into it.
What does 1.5 kilograms of water weigh?
Because if you use 1.5 kilograms, then you can say
This is
that
like-
the time is a second.
Yeah, they're saying like
It's kinda weird.
1.5 kilograms of water is hitting the car every second. So it's kind of like the time is 1 second and the mass of the water is
1.5.
1.5.
Those are some sneaky shenanigans.
Does that make sense though? I mean, if you say it, if you kind of say it out loud to yourself, it does make sense, I think. So then that's going to be the force. So what do you get? Let's see.
30.
Why is it negative?
Subtracting and
Because you're losing momentum as it hits the car.
Read the question again. What's it say? What is the force exerted by the car on the water?
Yeah.
Here's the car.
So
Which way is that force going?
The other way. Because it's stopping the
The car's exerting force that way on the water, so it makes sense that it's negative, doesn't it? Okay, I think we'll stop there. We'll do a bunch more tomorrow.
car with a potato.
Well, you know my art skills are famed.